here to give this talk. This talk is a study of my last 3 years, honestly. It is one of the longest study I ever conducted on a single subject. The reason was not because of Turkey or the related problems, mostly it's because of me coming back to Turkey, him, Rob, the owner of the idea, is switching between two places, between Oak Ridge to Ames and back to Ames at that. He became the head of the Oak Ridge National Lab Neutron Scattering department. Then he stayed there 1 year. After that, he moved back to Ames because of the political reasons. You can easily guess. Like Turkey, every other high-ranking officials in the United States have a tendency of switching places depending on the head of the government. He did not like neither us, I believe, the current president. Anyway, Rob is the owner of this project, actually. I'm only the workhorse, I can say that. Ashish Sapkota is the PhD student, my previous PhD student, in my Ames laboratory position. I was working before in Ames laboratory, before I switched to ITU, Istanbul Technical University. And this emptiness is because of the weird regulation that I do not understand why it is there. TÜBİTAK does not like us to put its emblem over there. I have no idea. All of the money, almost all of the money is paid by the US taxpayers and yet obtained from this department. And if I don't put their emblem over there, I will be in trouble. I have no idea why TÜBİTAK does not like his emblem over there. Anyway, this is the other PhD student whose work becomes absent in the time. Another scientist from Ames laboratory who helped at the last bit of the research. I'm going to show it. I'm really proud the result over there. Alan Goldman and Andreas Kreising are my best friends from Ames laboratory. He is the old department head of Ames laboratory, Alan. They are working as the co-chair with Rob, the head of the neutron scattering group over there. David Johnson is a brilliant guy who has a perfect understanding of susceptibility and magnetization data. You give him one data and he produces several pages of article to you. These are three guys that I don't know by face, unfortunately, because for the data collection, which is very simple thing, I cannot say that it is an experiment. Inelastic powder scattering is done by those three guys in Oak Ridge National Laboratory. Beamline name is ARCS. Let's go to the motivation. Now, we know there are two main superconductors at the moment. Main means everybody started to think about them, thinking that, hey, I'm going to solve this problem, solve the Hamiltonian, and declare my next stage of Einstein for the next couple of 100 years and get the room temperature superconductor. But it didn't happen, as we all know. The motivation is to find a bridge material between local moment copper-based superconductors to itinerant moment iron-based superconductors. Because they are, in this talk, I don't have one slide for it, but they are coupling each other very well. They are similar, they have similar behaviors, even though they are different material altogether. Copper-based superconductors are mode insulators. What does it mean? As a theoretical person, I'm not, but the other guys, when you solve the Hamiltonian, you got an equation for the electron motion, and you say that, hey, this material needs to be metal. But it is not. it is semiconductor, it is antiferromagnetic material. Copper-based superconductors behave like that in a normal state. Iron superconductors are metal, on the other hand, and I listened a talk when I was in my first postdoc position in McMaster University in Canada. The theoretician, professor, I believe, comes from, again, Oak Ridge Laboratory, and he was very keen. I was simply jumping on the stage saying that, hey, this is the metal in the room temperature, and we are going to, I'm pretty sure, he said, we are going to find room temperature superconductor with iron superconductors, iron-based superconductors. It didn't happen. On the contrary, the highest temperature without the pressure is around 50 Kelvin compared to 92 Kelvin without pressure, compared to 133 without the pressure for copper-based superconductors. As I said, manganese has a local moment, and barium, this material, in fact, does not have a coupling to a superconductor. It is not a father or mother of a superconductor material. It is close to a superconductor material when you replace Mn with Fe. Fe is itinerant, Mn is local. That is the bridge which couples to the bridge local moments of coppers in, let's say, YBCO, well-known superconductor. That is the motivation. Second motivation is show off of Robert, because he is the first guy who started to write the Hamiltonian in Fortran language. And he told me that this project has like 10 or 15 years of backward study of the Hamiltonian that he managed to run the Fortran, semi-quality run, because when he introduced me the Fortran code was a mess. It was not working properly. I need to go each line one by one. I'm very glad that, because when I joined to ITU, the first thing that they asked me to teach Fortran class for the first year students. And I was very okay with it. I'm still okay with it. I like Fortran, even though it is a rather difficult language to deal with. But don't understand me wrong, because we didn't finish the job with Fortran. I only calculate the Monte Carlo calculations for Fortran. The rest is on MATLAB. MATLAB basically calls Fortran. That is the details of the computational part of the job. I didn't give information on the slides. MATLAB calls Fortran. Fortran calculates the for the parameters that you feed the Fortran code for the Monte Carlo calculation, get the integral, get the intensity, and MATLAB basically puts on the pictures of the Fortran code, and with a simple chi-square test, we simply select the best of it. That was the first idea after our first meeting with Rob, how we regarding the idea of how we approach this thing, and at the end of the meeting, I'm pretty sure that I can rewrite the code in MATLAB and fit without calculating so many different things. I'm very glad that I didn't do it, because we will see it is almost impossible to get the fit. At least for this material. The third is less critical, the chemical doping effect of potassium, because the crystal is available. You do not need a powder investigation for it. And the idea, again, is to show that a single crystal work can be done without a need of a single crystal. That is the punchline, the last important part of that work. And I'm very happy that after 3 years of writing the article 7 times, 8 is missing. I'm not so sure, like the missing Levant 3 and Levant 2 in Istanbul. There is Levant and there is Levant 4. I have no idea Levant 2 and Levant 3, what happened. There are? Yeah. Oh, really? I didn't know that. Please teach me. I always thinking when I get the metro there. In 8, the version of the 8 of the article is missing, but there are several different, 7 different versions of the article. The 9th was published one there. But it was a good article. I'm very happy that I was involved. So, barium manganese arsenide is this material, the single crystal. It is a body-centered tetragonal, I4/MMM, triple M. As you see, the difference between A to C is huge, the lattice dimension. That means anything over this magnetic Mn plane is mostly a plane. It is not talking with C direction. So we can easily see that by just numbers, that is a quasi two-dimensional antiferromagnetic material. It is G-type. G-type means those names are coming from renormalization group. G-type means each next spin is opposite to the other one, the original one. So that is opposite to that one, that is opposite to this one, and that one, nearest neighbors, not the next nearest one. And that is also opposite to the, in the C direction too. Our Hamiltonian is this. As you see, it is here, antiferromagnetism is if J's are positive. I simply take the positive one. That is the real, the main effect of XY Heisenberg antiferromagnetic coupling. This coupling simply produces a kind of frustration on the first one, because this is next nearest one. This is the antiferromagnetic along C direction. And this last article is there for defining the LS coupling, uniaxial coupling of single ion anisotropy in other ways. The sum of the pure material has been analyzed in this article in 2011, and Jagat has analyzed the single crystal of it after the powder. Now, why do we need a second time for analyzing the same thing? Because in this article, to be honest, it's a little bit shame for Rob, but Rob did not fit the data. He calculates for several J's, and intuitively, or a little bit feeling, he chooses one J set and say that, oh, that will be the best one, nothing else, and he published the article that way. Now we really calculate and find out what is the chi-minima value and what can be the best J coupling values there. Anyway, now we are going to put this Hamiltonian, rewrite them, Holstein-Primikov representation. I hate quantum C. That is the quantum C thing, information in my background. And take the Fourier transform. Fourier transform helps you to introduce lattice in it. And by lattice, we have these two, in plane mostly, and out of less information there. And we get a energy equality, equation of motion, in other words. And we fit that thing. And also we get the size, cats of the Hamiltonian. And this is the first approach to the data. Second approach data is this, using damped harmonic oscillator. If we can manage to get three-dimensional data into a two-dimensional data, we can fit playing with the energy is the X value, abscisca value for E. We can use damped harmonic oscillator and find out the gamma, spin wave, spin gap values of S of QE. What they are going to give me, gamma value gives me a Hall effect results. If I introduce a hole into the Fermi surface of this material, there will be more carriers in the system. That means the damping oscillator damps more on the spin waves. So gamma needs to be increased. And the spin wave needs to be smeared, disappears. this is the idea to use the second way. First glance to the whole data. Whole data is this. As you see, that is a three-dimensional data. This is not a point detector scattering experiment. That is an inelastic powder experiment, which basically covers the detector range is a semisphere of detectors, so many different, so many in numbers, so many of them there in the 2 theta arm. And once when you collect the data, you collect all of it, all possible information over there. As you see, this is a momentum transfer line. You can think that it is 2 theta line, okay? 0 to 15 inverse Armstrong. This area is around 30 degrees, mostly 110 degrees around over here, mostly. As far as I remember, I'm not so sure though. This is the energy transfer line. As you see, we have for this data from 0 to 100. This is 150 data. I cut 140 there. And this is the line that everybody thinks that this is a powder scattering experiment line. Elastic channel. This is not an elastic powder scattering experiment. This is inelastic powder scattering experiment. And honestly, we might be in the days of like 1920s now in physics, when X-ray is found that it scatters from powders, and people start to think about what that information can be, how can it be analyzed, and what information they can get from the powders when the X-ray scatters from the powders in 1920s. That is the almost stage for the inelastic one, and we are, thanks to God, for me as well, is the pioneers of this now, because that analysis has not been done, as far as I know, rather than this group, including me, before. The Fortran code is on the repository in the NIST laboratories and Oak Ridge National Laboratories repository server machine. You can download it, but honestly, I can assure you that you will not understand any of it, even if you spend like maybe months. I'm not so sure how good you are at Fortran, but it's not just the goodness of the Fortran or the language that you know. This is basically how you approach the code. There are so many different parameters that you need to feed. So it is really, really the baby step primitive level of the analysis now. But hopefully in the time it will be easier. As you see in the whole data, there is magnetic information over here. If you see a scattering when it is different than E equals 0, which is elastic line, it is magnetic information. Nothing can be happening. This part is also can be magnetic, but it is not. As you see, the line is increasing in intensity as you go to higher theta angle or higher Q values. That is phonons. Phonon do that. Phonon structure does that. So that increase is mostly quadratic. In that area, it is all phonon. But there is intensity over here too that we need to think about. So when I received the data, I said that I'm going to cut the data over here at 10 millielectron volt. And I'm going to cut over here for the momentum transfer range and take all that region for the magnetics region. And that is how I did it. As I said, I cut a little bit less than 10, as you see. Actually, it should be 10. That is my mistake. That is 10. That is 50. That is 140 there at the top. 0.5 is the lowest Q value, and the 4 is the highest Q value in this data. Now we have steep magnetic, like chimney wise of intensities there, and the intensity disappears over here, but repeating with the Q distances. That means it is magnetic, the first principle, and the second are the other reflections of magnetic as the magnetic form factor cuts exponentially. That is the whole data that I showed before. Now, that is 75 more resolution-wise data. As you see, we cut a little bit over here intensity, so it is not good to use 75. It is better to use 140 data there, 150 data. And that is for pure, that is for 12.5% potassium dope. Potassium dope is done on the, where is it? On the barium place. But the idea was to take some effect on the magnetic lattice structure. Okay. This is the 25% of the potassium. Now, we got this thing, the energy equation over here. Then we start fitting the data. The fitting basically uses a Monte Carlo integration routine. We fit the Monte Carlo integration routine for the primary case for 5,000 Q, random Q values between 0.5 to 4. That means it is a powder scattering. So each Q value for each 2 theta arm, 2 theta value, other ways of saying, there is a sphere, and those sphere basically scatters on the detector. And we have in the preliminary 5,000. After the preliminary fits, when I get the best values of chi-squares for the preliminary, I decided to go like 30,000, sometimes 50,000 Q values, and recalculate the best like 10, 15 chi-square values, and get more precise values of Monte Carlo. As you know, Monte Carlo technique is a random selecting abscisca technique to calculate the Y values, depending on the abscisca values. If you have a less limited number of Monte Carlo seeds, you will have a big difference in each iterations. So I need to get that differences as much as small by introducing so many, like 30,000, sometimes 50,000 Q values. This is the data, that is my analysis. As you see, it looks like very well to the data. And as you see, you may see some background changes there too, and there as well. That is pure 12.5%, 25% potassium. So we realize altogether that not only taking the correct or having the correct intensity for the magnetic scattering, but also, maybe more, having a perfect definition of background is crucial for the goodness of the fit. So what we do is basically define the background. I'm going to go to that the background definition on a next slide, coming slides more in a minute. Define a background, and the definition of the background is basically moving a high Q value where everything is phonon dominated, and carry that thing to the low Q value region by scaling it. As I said, the intensity starts from here to goes there by quadratically Q to the power 2. When you average, for example, 10 to 15 Q, the intensity in this line, and carry that intensity to there by quadratically, dividing by Q to the power 2 values, you may subtract here and get more intensity for the magnetic one. Or the way that I did, you basically calculate the magnetic information and put on the background and find out almost the same fitting behavior. Especially if you look at that, there is an intensity here, and that intensity is caught in the analysis. This is not a phonon background intensity, that is unreacted manganese oxide. Manganese 1, oxygen 1. Manganese 1, oxygen 1 is also antiferromagnetic material. We will see it later. Now, as you see, I calculate the numbers over here. J's are for pure material is this. The previous article, 2011 article, were RAP did not fit the values, are very close to it, thanks to God. RAP was almost correct, but not really. It is in the error bar, very close to the error bar. Error bars are basically touching to each other. However, those numbers are better for pure material. For 12.5, we have those, and for 25%, we have those values. The second number over there is the antiferromagnetic transition temperature, Néel temperature, 625, 611, and 575 Kelvin. As you see, when you dope the material, you lower the TM values, which is all okay and expected. Corresponding number is the Kelvin to millielectron volt, the same number, 5 minutes. The third number is the one that I calculated for the temperatures. Now, the second damp harmonic oscillator is, instead of putting the number over there, instead of putting the phonon background on my magnetic region and define a background, we subscribe the phonon background, and also we subscribe the, a Gaussian which is fitted to the elastic line. And yet, at the end, we get a two-dimensional order parameter kind of intensity. When we fit those things with this information, the one that I showed over here, we finally get gamma values and the sigma values, spin wave, gap. As you see, it is the gap over here. And the gamma values, damping values, in other words, inverse lifetime of the spin waves. We got some numbers, but honestly, those numbers are not the one, or the thing that we are looking for. They don't tell the thing that we are looking for. Gamma needs to be increased by doping. Sigma needs to be decreased by doping, but they are not. However, it is still okay because TM does not change. That is basically 8% of changing of the whole to pure to the that one, 25%. So it is still okay. So back to the background calculation, as you see, we have that background at the end. We fit the high part with the quadratic information between 6 to 8 Armstrong, and even I fit more part. And also quadratically, I carried the fit values back to the interested region there. This is the whole scattering for manganese oxide. We also calculate that thing with the same code that we wrote. And when we add all together, this happens, and that is basically there on the beneath. So that is also a good way of comparing but I'm not going to go to details. This is the idea of taking the two-dimensional data and respect to my calculation. If you ask questions, I'm going to tell the details. That is whole picture of how they fit each other. There are things that we miss, that is obvious, but that is inelastic scattering, is an elastic scattering, and we are the first. And this is, as you see, the chi-square best values valley. The previously RAP's articles, first articles values are there, very close to mine. Mine is around here. And this line, when I calculate the equation for that line, basically represents, it can be shown by the spin wave values, as in this graph too. If you go and by eye take the triangular over there and get the slope to e to the q values, you will get spin waves, steep spin waves in the number of 222 and around. And I get with the this is mean value approximation. Those equation was done by David Johnson. And I got almost very close to those numbers, as you see. And these are the numbers that is represented over there for j equals 0. And that is the confirmation of my talk. The manganese oxide, unreacted manganese oxide, was fit in my background here and scaled to there. And the scaling gives me exactly exactly the same numbers of this magnetic X-ray diffraction analysis. This is done as the last point of my research. When we tried to publish the data 6 months ago, the referee asked us, you have to put this data, otherwise you cannot publish the, he doesn't like without that thing there. And we, Pandev, my friend over there in Ames, did the experiment, XRD, and when we fit, this is pure, it is 12%, it is 25%, as you see, the intensity increases. The intensity ratio is exactly the same intensity ratio that I got from my inelastic scattering analysis. And that is the whole conclusion. Hole doping does not change so much. We have encountered uniqueness problem, yeah, but we've successfully managed to calculate manganese oxide impurity ranges with inelastic scattering data. X-ray diffraction confirms that thing. No ferromagnetic signature was found. It is hard to define a ferromagnetic signature from powder. It's also another thing. Another successful analysis of inelastic neutron scattering data. Thank you very much for your attention.
Sınırlı bir soru alabiliriz. Hocam tekrar teşekkür ederiz. Buradasınız. Daha konuşma imkanı oldu.